Here's a diagram of a point that is in quadrant 2, labeled with both its rectangular and polar coordinates. Now if we look at this, notice it's a right triangle, and so all of the right triangle relationships apply. For example, we have the Pythagorean theorem, x squared plus y squared equals r squared. And we have SOHCAHTOA. We can say that sine of theta is equal to y over r, opposite over hypotenuse. Cosine of theta is equal to x over r, and tangent of theta is equal to y over x. We're going to use those relationships to go from polar to rectangular and rectangular to polar. Now many students, when I write this, say, wait a minute, you've got theta outside the triangle. Don't you want theta inside the triangle when you write trig functions? That's a very good question. Remember that we used to call this angle theta reference. That was because that angle is the angle we sort of refer to when we draw the triangle that gives us the trig ratios for this angle. So for our actual angle, the reference angle provides the triangle that we use. But we're actually finding the trig values of the angle outside the triangle when we do this. So let me give you an example. Let's say, for example, that theta is equal to 130 degrees. That means the angle in the triangle, theta reference, is 50 degrees. Let's see what happens when we apply the sine and cosine ratios to this. So we could say that sine of 130 is equal to y over, and I need a value for r. So let's think of a value for r. How about let's let r equals 18 for no particular reason. Okay, so let's just say r is 18. Now, if I wanted to find the side y, I could say sine of 130 is equal to y over 18. So 18 times sine of 30 is y. And I could also say 18 times cosine of 130, so I said 30 instead of 130, of 130 is x. Would it make a difference if I use 130 or 50? You're probably saying, yeah, it does make a difference, but which one is the right one to use? Do I use the 130 or do I use the 50? So I'm going to open this up and just show you that I did this on the calculator. 18 times sine of 130 and 18 times sine of 50 actually give me exactly the same number. That would give me the y, that y is 13.7. If I do 18 cosine of 130 and 18 cosine of 50, notice that I get the same number, but one's positive and one's negative. This one is the one that I would want to use for quadrant 2, because in quadrant 2, x is clearly negative. So if you use the reference angle, the angle inside the triangle, you will always get positive values for all of your trig ratios. However, you don't want positive values for x and y in quadrant 2. So it's actually better to use the angle outside the function, the actual angle that we're referring to, rather than the reference angle when we use our SOHCAHTOA in polar coordinates. Okay, so let me move this down a bit here, and let's fill in what we need to do to get from polar to rectangular, because we've just done that. To go from polar to rectangular, we're going to use these two relationships. So polar to rectangular. We're going to say sine of theta equals y over r, because I know theta and I know r. And cosine of theta is equal to x over r, because I know theta and I know r, so I can find x. So x then is going to be r cosine theta, and y is going to be r sine of theta, and use the actual theta, not the reference angle. Now, you can use the reference angle as long as you remember to put a negative sign where needed on either x or y, but students tend to forget that, so I say using the actual angle is actually more helpful. Okay, now what if we want to go to rectangular to polar? We know x and y, and we want to find r and theta. So I want a way to find r using only x and y, and I want a way to find theta using only x and y. So notice these would be the two relationships I would use if I want to go from rectangular to polar, because x plus y, this gives me x and y and allows me to find r, this gives me x and y and allows me to find theta. So my two relationships I'm going to use are x squared plus y squared equals r squared, and tangent of theta is equal to y over x. So to find r, I'd be doing the square root of x squared plus y squared. To find theta, I would be using inverse tangent of y over x. Now, I do need to remind you of another thing, that when we do inverse tangent, we don't always get the angle that we want, because inverse tangent has a limited range of angles. It only gives me quadrant 1 and 4 angles. So if I want a quadrant 2, or a quadrant 3 angle, I would need to add 180, or in this case we'll say pi, because we're dealing with radians mostly. If I'm in quadrant 4, I would get the correct angle, but I would need to add 2 pi to get a positive angle. Let me show you again why that is true. Let's say we're trying to find a quadrant 2 angle. So we know this is a negative x here and a positive y. And I'm trying to find this angle right here. There's the theta I want to find. Well, when I do inverse tangent of a positive y over a negative x, I'm going to get an angle actually in quadrant 4, because this also has a ratio where y divided by x is negative. Only in this case, y is negative and x is positive. So what the calculator will give me is this angle. What I want is this angle. The difference between them is 180 degrees. So if I take the negative angle in quadrant 4 and add pi to it, or 180, plus pi or 180, then I'm going to get a positive angle in quadrant 2. Now, what if I have an angle in quadrant 3 that I'm trying to find? Well, here negative y's and x's are both negative. If I do inverse tangent of negative y over negative x, that's the same thing as inverse tangent of a positive y over a positive x. So it's going to give me a quadrant 1 angle. It's going to give me this angle right here, where I have a positive x and a positive y. Once again, the angles that I want is this angle. I want the angle that goes all the way around. So how far are they apart? They're apart 180 degrees. So I would need to add pi. So add pi, or 180, to the quadrant 1 angle to get the quadrant 3 to get the quadrant 3 angle. Now the only other thing I would show you is if I am in quadrant 4, and let's say I want to be in quadrant 4, and I get this negative angle, I could add 2 pi to that. And if I add 2 pi to that negative angle, I would get the positive angle in quadrant 3. So that would be the only, if I wanted to go from positive to negative. So now let's look at 2 examples. We're going to take the point that we plotted on the original notes on the previous page. There's my point, 8, 2 pi over 3. Just to double check, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then we went around to here. Okay, that's 8, 2 pi over 3. I want to put this in rectangular form. Well, you're not always going to have a grid, like a nice polar grid, nor would I expect you to draw one by hand, but I would expect you to make a little sketch showing where that angle is. So let's recall pi over 3 is about 60 degrees. That is 60 degrees. 2 pi over 3 would be 120. So the angle I'm talking about is about right here. So this is 2 pi over 3. The radius then would be the distance from the center out to the point. So here would be my point. Now I want to find the x and y coordinates of that same point. So that would be going over to the left, x, and up, y. So here would be my x and my y. Now notice my x is going to be a negative number. Also, x should be a smaller length than y, based on the way I drew my triangle, because this is a 60-degree angle right here. So the y should be bigger than the x, and the x should be negative. So applying what I know, if I know r and theta, and I want to find x and y, I'm going to use sine and cosine. I'm going to say sine of 2 pi over 3 is equal to y over 8. And cosine of 2 pi over 3 is equal to x over 8. Then I can solve for x and y. I'm going to kind of get this out of the way here. So y, well, let's just do x first, because I typically put x first in the point. So x is equal to 8 cosine of 2 pi over 3, and y is equal to 8 sine of 2 pi over 3. So notice I'm using the actual angle, not the angle in the triangle, which would be a 60-degree reference angle here. In radians on the calculator, you do need to be in radians to do this. This is what you end up with. So make sure you are in radian mode. So in radians. Pi, remember, you can find on the pi button in your calculator. So here's the correct answer. So the point that I get is -4, 6.928. Now something I want to ask you to be able to do is to verify that the coordinates that you get when you go from polar to rectangular or vice versa both make sense. They both get you to the same location. So let's superimpose an xy coordinate system on top of our polar coordinate system. If we do that, call that y and we'll call this x, I want to go -4 in the x direction. So we'll use our little concentric circles to help make our tick marks. So there's 4. I want to go up 6.9. So let's go up about 7. 1, 2, 3, 4, 5, 6, 7. So there's 7. Now, if I were to go straight over from about 6.9 and then straight up from 4, there we go. That point makes perfect sense. It's in the correct location. Now, let's go the other direction. Let's say I want to, get that little, oops. Let's say I want to write -2, -7 in polar form. So once again, let's make a sketch of what we have here. This is in quadrant 3, -2, 1, 2, 3, 4, 5, 6, 7. So the point's about right here. Now, in polar form, that would mean I would have this radius and this angle. This would be my theta. And so I'm looking for r and theta when I know x and y. So I know that x is -2, and I know y is -7. So the two relationships I'm going to use are -2 squared plus -7 squared is equal to r squared. So r is equal to the square root of 4 plus 49, or the square root of 53. And I'll calculate that in just a minute. One thing I do know, though, is that the hypotenuse has to be the largest side. So this value has to be bigger than 7, because 7 is the length of the largest side, so this has to be bigger than 7. And we know it's bigger than 7 because the square root of 49 is 7, so clearly we're okay with this. Now the second relationship I want to use is tangent, because I know that tangent of theta is -7 over -2. So theta is equal to inverse tangent of 7/2, or -7 over -2, but it's positive 7/2. So what do we end up with? So I did this on the calculator earlier, so I'm going to open this up for you to see. So square root of 53 is 7.28, which is a little bigger than 7, which is perfectly good. And then if we look at our inverse tangent, there's our inverse tangent. I'll put this down here. Notice we get 1.29. So let's recall radians from our earlier work in semester 1. Remember, a radian is the length of one radius measured around the unit circle, and or the angle that cuts an arc that is equal in length to the radius of the circle. Also, you may recall that 1 radian is approximately 57.3 degrees. So 1 radian would be in quadrant 1 right here. 2 radians would be close to 120 but not quite. 3 radians would be close to 180 but not quite. Remember, this is 3.14 radians, pi. 4 radians is close to 240 but a little less. 5 radians is close to 300, and 6 radians is close to 360 but not quite. So there's where our radians would end up. So if I'm looking at 1.29 radians, 1.29 radians is probably about right here. The angle I want, notice, is back here. So look at my angle here. It's a pretty steep angle in quadrant 3. So to get from one to the other, I'm going to have to add 180, or in this case, add pi. So if we add pi to this number, we end up with 4.43 radians. It's the 1.29 plus pi. So the coordinates of my point are 7.28, 4.43 radians. And we have verified that that does make sense. Now that you have learned to plot points, you will be able to plot points when we have a polar equation and see what kind of graph it makes. So that's, other than doing plotting some points and converting back and forth between polar and rectangular, you're going to also have your first exposure when you do your homework to graphing a polar graph.